Okay, today's going to be a relatively short lecture, just looking at galaxies and the foundation of modern cosmology. And so I'm going to talk about islands of stars, basically talk about the three different types of galaxies that are found in the universe. I'm going to jump over measuring galactic distances because there's a lot of math there, so I'm just going to skip that. But then I'm going to talk a little bit about the age of the universe, which we talked about way back in the beginning of this course, astronomy, way back in chapter 1, when we talked a little bit about the raisin bread and how you bake it and it expands and galaxies are moving away from each other. So let's jump right into islands of stars. So galaxies, they're kind of considered islands and stars because they're made up of hundreds of billions of stars. So the lives of galaxies is connected with the history of the universe. So I'm going to talk about the Hubble Deep Field here, which states that a galaxy's age, distance, and the age of the universe, they're all closely related. And when we study galaxies, basically we're looking at cosmology, the study of structure and evolution of the universe. And Hubble Deep Field means that the deepest images that we've ever gotten from distant galaxies are billions of light years away. So we're actually kind of like looking back in time. Now there are three major types of galaxies: a spiral galaxy, as you can see here, an elliptical galaxy, and then irregular galaxies. And so I really like this picture because you can actually kind of see the shapes of all these different galaxies, and they're just zooming in on the three types. But spiral galaxies have a disk and spheroidal components. In this case, this is a barred spiral galaxy. Sometimes they just have multiple arms coming out, and sometimes it looks like they have a bar in the center here, like right across the bulge. Another form of a spiral galaxy is a lenticular galaxy. It has a disk, just like a spiral galaxy, but it's just not as dusty. So it's actually an intermediate between a spiral and an elliptical galaxy. But the elliptical galaxy has the spheroidal component, but no disk component. So it kind of just looks like a big sphere, if you will. A lot of elliptical galaxies, if you see them in red, yellow, means that the stars are very old. The third type is an irregular galaxy, and with irregular galaxies you tend to see a lot of blue colors, which means that there's ongoing star formation. Now galaxies tend to be grouped together in two ways. So spiral galaxies, and they've just noticed that with every spiral galaxy they've observed in our universe, they tend to be found in groups, just like a few dozens. But when we look at elliptical galaxies, like in this picture here, you see them in huge clusters, maybe hundreds of thousands of galaxies grouped together. So it's just kind of a unique grouping that you find with the two types right there. All right, the final thing I want to discuss is the age of the universe. You guys know that the age of the universe is about 14 billion years old. And so I want to talk a little bit about Hubble's law, which means that the faster a galaxy is moving away from us, the greater its distance. This kind of ties into that raisin bread analogy that we discussed at the beginning of this course. And they've noticed that the expansion rate appears to be the same everywhere in the universe, and that really the universe has no center and no edge at all as far as we can tell. And so with the raisin bread analogy, there's a center and there's an edge. So we're going to throw in a different analogy that explains Hubble's law and the rate of expansion a little bit faster. So one example is to look at maybe a balloon. So if you take a balloon and you put dots on it, and then you blow that balloon up because then it's expanding, like there's really no center or edge. It's just the surface of the balloon. So it's kind of a better analogy than the raisin bread analogy. Okay, the cosmological principle is actually kind of a unique thing. I was just going to find it here. It says here that, okay, so first off, the universe looks about the same no matter where you are within it. So if we look at matter, it's distributed in very large scales across the universe. There's no center or edge, and this has not been proven beyond a doubt, but it's very consistent with every observation we've pretty much come across. And it does tie in something called Hubble's constant, which is found in Hubble's law. See, with discovering how fast galaxies move, they talked about Hubble's law, and there was just a lot of math behind it. But in that Hubble's law, there's a Hubble's constant that helps us tell the age of the universe because it relates with its speed and direction as well as distance. So I know this is kind of weird to think, like our expanding universe is basically a bunch of ball of galaxies expanding into nothing. But to the best of our knowledge, the universe is not really expanding into anything. As far as we can tell, there's like no edge, no, to the distribution of galaxies in our universe. On very large scales, the distribution of galaxies appears to be relatively smooth, as I mentioned in this first bullet point here. And the idea that the matter in the universe is evenly distributed without a center or an edge is basically the cosmological principle. Although, like I said, we haven't proven it to be true, but it's very consistent with our observations. Yeah. Okay, so this diagram, we know that it takes a long time for light to travel when it's really, really far away, when the object is really, really far away. So this is a space-time diagram for a supernova in a distant galaxy. And it's saying that the look-back time to the supernova is 400 million years, because maybe that's how long it takes the light to reach us. So when we look at it today, this is what we see, because the photons are traveling, but really where it is today location-wise is 400 million light years that way. So we're looking at galaxies kind of like in this look-back time rather than where it really is today. So when that light travels, as the universe expands, photon light wavelengths do stretch like wavy lines on this expanding balloon. And these light waves tend to stretch to longer wavelengths as the universe expands, causing a cosmological redshift. All right, final kind of question here. Why does the observable universe have a horizon? So when we began our discussion with the expanding universe, we stressed that the universe as a whole does not seem to have an edge. Yet the universe does have a horizon, a place beyond which we cannot see. And so the cosmological horizon that marks the limits of this observable universe is a boundary in time, not in space. It exists because we cannot see back to a time before the universe began. So like if the universe is 14 billion years old, then no object can have a look-back time greater than 14 billion years old. So thus the age of the universe fundamentally limits the size of our observable universe. Okay, so yeah. So in summary, we talked a little bit about what cosmology is, the study of overall structure and evolution of the universe, the three major types of galaxies: spiral, elliptical, irregular. How galaxies are grouped together. With spirals, they're in groups of several dozens. With the ellipticals, they're in clusters of hundreds to thousands. We skipped over galactic distances. And then I talked a little bit about Hubble's law, but not a lot, just saying that the more distant galaxies are moving away faster, and there's a Hubble's constant that helps us determine distance from speed, and then we can measure that with a Doppler shift, and then how Hubble's constant ties into the age of the universe, and then the look-back time with the cosmological redshift. So